Stanford University.
Well, thank you, Sally, and certainly appreciate the invitation. I have never been called the perfect thing before. That's good. I'm going to give you quite a wide variety of information. Thank you for coming on a day like today. I'm going to look at shale gas, some of its realities, what we think is going on. I'm going to go all the way from a very high-level 50,000-foot view all the way down to the molecular level. And if the molecular level starts to drag a little bit, if I see eyes glazing over, I'll speed that up because it is the dreaded chemistry. So if you haven't had chemistry in a while or don't care for chemistry, we do need to touch on a little bit. Shale gas is very new in the press. It's very new with policymakers right now, but it's actually the oldest source of natural gas in the United States. The first gas well in the U.S. was drilled in 1821, significantly predating the first oil well by Colonel, with a small c, Colonel Drake. It was drilled in Fredonia, New York, and it was used to illuminate the town. And there was a visit in 1825 by a gentleman with quite a bit of history to this country. And if you go to Fredonia now and you go look in the yard, it says that the town was illuminated in honor of the visit by General Marquis de Lafayette in 1825, who was one of our Revolutionary War heroes. So this goes way, way back in time. Now, the first shale well, the first gas well, something we're still trying to figure out today. The reason it's so much in the news now, the reason we have so much productivity, is not because we just found these shales. We've known about them as a source rock, as gas in place for a very long time. What's happened is that technology and demand have allowed access to this resource and turned it from gas in place to very much a producible resource or a potentially producible resource. So that's what I'll be focusing on today. We seem to be having a computer. What it says at the top is 2007, where are the Haynesville and Marcellus? Just going to take a look back 2 years from now. Shale gas now supplies about 10% of our daily production in this country, 10%. Coal bed methane is also about 10%. We'll see that in the past, people thought coal bed methane would continue to ramp up and shale would keep at a low level, but that hasn't happened. Shales come forth very quickly. Some people may not realize that in addition to this 1821, shale gas and coal bed methane go back even further. Are there any fans in here of the original Star Wars? Okay, got a few? Well, you may remember when Obi-Wan Kenobi turned to Yoda when they thought Luke was going over to the dark side and said, "That boy was our last hope." People don't realize that Obi-Wan was really talking about coal bed methane. And Yoda said, "No, there is another." And it wasn't really Princess Leia, it was shale gas. But actually, there's even more things coming down the road. We do have a very diverse natural gas supply in this country, not just shales, not just coals, tight sands, conventional reservoirs, carbonates, etc. But in 2007, these were the main plays. There's the classic shale plays, which were at a pretty low level. Whoops, excuse me. Here in the Appalachian Basin, the Ohio Shale, the New Albany Shale in the Illinois Basin, the Antrim in Michigan, the Barnett down here in the Fort Worth Basin, and the Lewis Shale in New Mexico, not to be confused with the Lewis Shale in Wyoming, which is actually a turbidite, for those of you who don't know geology. So this is where the shales were. The Haynesville, big place making the news now, is located down here, and the Marcellus runs up through here. Now, geologists knew these formations existed, but they weren't very attractive reservoirs at the time. Again, technology has moved them forward in just a couple of years. Well, in 2007, the Energy Information Administration of the Department of Energy made a projection. The blue is real production. This is 500 BCF. This is 1,000 BCF, or 1 trillion cubic feet. The U.S. produces about 20 trillion cubic feet a year. We buy another 3+ trillion feet from Canada. So we're about 23, but we produced 20. And they thought that, well, by 2007 or maybe 2011, the shale gas would account for 1/20th of our required production. And actually, right now, we're sitting at 2 TCF. So this projection in 2007, a forecast, it wasn't meant to be truth. It's just given certain assumptions, this is what could happen. The forecast was wildly underneath what turned out to be reality, with shales now producing, again, 10% of what we need. If you take a look at historical shale gas production before we get into the big picture, 1979 to 2007, this was the Appalachian Basin. This was the Michigan Basin. These little guys here were the Lewis Shale in Indiana, and this was the Barnett Shale in Fort Worth. It started taking up, this is getting close to a hockey stick. I'll show you a real hockey stick in a minute. Barnett production taking off, but it took a very, very long time. So people didn't consider that the Haynesville and the Marcellus would become so productive so quickly. A key question is, will they remain productive? Well, the shale gas didn't just show up from 1821 up till today. There has been a great deal of research expenditures, both in the lab and in the field, that have focused on shale gas. Some of it out of your pockets, taxpayer money out of the Department of Energy. Some of it out of natural gas users' pockets from the Gas Research Institute, Gas Technology Institute. And some very good work was done. Additionally, this has caused a frenzy of acquisitions, the most recently being when ExxonMobil just bought a company called XTO for $30 billion. And they will have a lot of access to shale gas as well as some oil from shales in the Williston Basin. And additionally, a great deal of money has been spent on developing the resource, the infrastructure, the drilling, the pipelines. So shale gas didn't just show up, although it's been relatively new in the popular press. One example of what it took to get there is shown by George Mitchell, who's now retired from Mitchell Energy. His company was bought by Devon Energy. He knew what he had. He knew he had all this gas in place in the Barnett Shale around Fort Worth and Dallas. But his engineering staff, as bright as they were, worked again and again and again to recover this gas. 1980 to 2006, and here's a hockey stick. That production in number of wells, 3,000, 4,000, 5,000. The Barnett alone now produces about 1 trillion cubic feet of gas. Many of the wells that were first studied, looked at, stimulated, fractured to try to get that gas to the wellbore were re-stimulated, refractured as technology improved, and they eventually got the formula right. So this is an example of a lot of smart people spending a lot of money and a lot of time to get something to work. But once it works, you can take that elsewhere around the world. Shale gas is becoming very much pursued in Europe, particularly in Ukraine, in Poland, in Germany, as well as in China and some other countries. Well, shale gas has a lot of exploration considerations. It's not an easy reservoir to work with, or we would have figured it out a long time ago. The question of natural fractures, these shales, these rocks are what we refer to as tight. They do not readily flow anything through them. They look more like this screen as far as their fabric. They're very, very low permeability, very low porosity. Sometimes fractures help that gas to flow to a wellbore. Sometimes fractures are a problem. So there's a question of whether they work. If the fabric of the rock, if the ability of the rock to transmit fluids and gases changes, then we can take advantage of that. There's also a matter going all the way back to the organic matter, and we call that kerogen, the parent material of oil and gas. What kind of organic matter do we have? Because not all organic matter is created equal. Most of the oil and gas on this planet came from single-celled organisms, bacteria, algae, and we have to have the right kind with enough hydrogen to generate this natural gas. And then the question comes up, was the gas generated in place by bacteria or by standard petroleum sort of thinking where you have organic matter deposited in a sedimentary basin It gets heated up, it changes to this kerogen, which changes to something with an even stranger name called bitumen, and then we generate oil and gas. So again, it's not an easy path to understand. How hot these rocks got and when is important. And finally, as we're drilling these wells, we'd like to be able to evaluate these reservoirs while we drill. Shales are called a resource play, along with coal bed methane and tight gas. That means, unfortunately, we have to drill a lot of wells to get the production that we need. If we can drill better wells quicker, we benefit from all aspects. One thing we do know about shales is that they are quite variable. This is a plot of some geochemical parameters, the amount of gas in place on this axis, the thermal history of the shale, how much gas is adsorbed or actually sucked onto the organic matter in the shale, how thick is it, and how much organic carbon. And what you can see even from the back of the room with these colors is that a variety of combinations of these critical parameters can still make a successful gas play. So we don't have a cookie cutter. We can't go out to a basin somewhere in the world and look for parameters X, Y, and Z and come up with something. There's also some surprises. This is known as a petroleum system chart or an events chart. What it shows is in the Antrim Shale in the Michigan Basin that the rocks and the organic matter were deposited back in the Devonian. And they had various things happen through them through time. But it was actually 10,000 years ago that the gas we produced was generated. 10,000 years ago. So what you have are microbes dining on a Devonian buffet. And that fact changes your exploration strategies. So there's all kinds of extra things that go on with these shales. Well, there are some things we know as we're learning about this, at what makes a successful shale gas play. If you want to have productivity within a shale gas system, we know we have to have thick enough rocks that have a significant organic richness, and you'll often hear in the press total organic carbon, or TOC. It's really not carbon we're concerned about. We have lots of carbon. We have too much carbon. We need hydrogen. We need the hydrogen because every methane molecule is 1 carbon and 4 hydrogens. It rapidly depletes the hydrogen supply in a system. So we need thick shales with lots of hydrogen that have undergone a good thermal history to generate a lot of gas in place. And then we also need the right kind of mineralogy which will impart a certain brittleness to the rock, that when we fracture these rocks, when we stimulate them, they'll crack in most cases and allow gas to flow to the wellbore. Having increased pore pressure helps. That is, it'll help the productivity, and I'll touch a little bit about that on the end of the talk. And having enough ability to flow, what we term permeability, to make all for the productivity. So the right kind of rocks with the right kind of history, with the well-behaved, that when we stimulate them, we get productivity. So that's what a shale gas play needs. So those are all big 50,000-foot sort of views on things. The actual rocks themselves are extremely difficult to characterize. They are so fine-grained. They have, we measure Darcy flow of water, through, say, a sand aquifer in Darcy's. These shales are in micro and nano Darcy's. So they are very, very difficult to flow gas through. So while we know the words, getting to characterize these rocks and see what we really need to do is another question. So that's a little background on shales. We've known about them a long time. We've known about the gas and the history. We can now tap them through technology. So let's take a look at how much gas we think is potentially reservoired in these shales. This is not an easy thing to do. What we're doing is quantifying the unknown. We're looking forward in time. Sally mentioned the Potential Gas Committee, the Potential Gas Agency. School of Mines has for a very long time helped the Potential Gas Committee, which is a group of industry, government, and academic volunteers, work towards estimating how much natural gas we have remaining that's technically recoverable. And there are 2 members of the Potential Gas Committee in the audience, myself and Jeremy Platt, who's an observer from EPRI on our board. These folks have worked together since 1964. Now, I wasn't with them in 1964. My hair hadn't turned good looking, and I didn't know anything about the natural gas industry. But since 1964, every 2 years, they've put out estimates that are geologically based on how much of the remaining endowment of natural gas we believe we have. So that's what I'd like to cover with you for a little bit. We're one of the only organizations that does this anymore. One thing to clarify, if you read the popular press, New York Times, Wall Street Journal, they kind of got the wrong end of the stick. Our group does not look at proved reserves. So if you read something that says we have 2,000 trillion cubic feet of reserves, that's not correct. We are talking about technically recoverable resource. Proved reserves have to do with existing gas reservoirs. You've drilled a well. You can touch out into the reservoir to a certain extent. And you have very formalized guidelines from an engineering standpoint and from the Security and Exchange Commission standpoint on what is a proved reserve. What we do, what we look at, is the resource base that is much larger that backs up these proved reserves. We're looking at discovered natural gas in existing fields beyond proved reserves to the limits of the reservoir. Looking at undiscovered gas, fields yet to be discovered, technology, and in some cases, the effects of economics. Well, the committee, when it publishes a report every 2 years, looks at 89 geological provinces and looks at 3 categories of natural gas, depending on how much geologic and engineering data we have. This is a summary slide of a 350-page report that shows what we think is where. The red is shales, carbonates, sand reservoirs, all the reservoirs other than coal, which is shown in black. And what you see is that the Gulf Coast has the largest amount by our work of the remaining potential resource, followed by the Rocky Mountains, followed by the Mid-Continent. There's a great deal of shale gas involved here and here. Oh, excuse me, got to put the Atlantic in there. A great deal of shale gas in these very large numbers. California, on the other hand, doesn't have the large natural gas endowment in this whole Pacific region up through Oregon and Washington. It's a function of the kind of rocks you have, it's a function of the geologic history, and it's a function of the abuse the reservoirs have suffered through time in this very active tectonism. If you look at our assessments through time, this is what caught everybody's attention last June 18th when we released our our report in Washington. These are the estimates of the committee from 1990 to 2008. This is 1,000 trillion cubic feet of gas. Coal bed is shown at the top and all the other reservoirs on the bottom. And you can see that we've slowly increased upward, say 100 trillion cubic feet, even though between each report we've produced about 40 trillion cubic feet. So this is a net increase every time. Well, technology's taken place, and what you see in 2008 was a very large amount attributed to shale gas. It turns out in 2006 we had about 1/3 of that amount attributed to shale gas, but for a variety of technical and social reasons we didn't break that out separately. For 2008 we evaluated a lot more shale basins, and we were able to move forward with a lot more, it's referred to in the business as granularity, on our resource estimate. So the 2008 estimate is significantly higher. A lot of that is due to shale. Technically recoverable resource. This is the most upstream look you can get. This is the geological endowment. This does not say when the resource will be produced. It does not say at what cost the resource will be produced. This is geologists working these basins for a living coming up with these values. But it does give us a baseline, and it gives us history going back to 1964 on our view of the resource base. So there is value there, I believe. Well, what could go wrong? What could keep shale gas from making a larger contribution beyond the 10% to the U.S. supply? Now, no one on our committee or reasonable people I talk to think that shale gas is going to be the end of the life of the gas industry. It's just going to take over. It's there, we're fortunate that it's there, but we have this other large number, again, a very diverse resource base in coals and in other reservoirs. We're going deeper technology is improving, and so the gas supply picture is pretty bright. Right now, gas supply is about 25% of the nation's energy, 25% in round numbers. Well, what goes on is to meet this demand, we don't think it's a concern about the resource base. We think that, again, it's diverse, it's very large, and we're in good condition there. But we have to be able to extract from that resource base in an acceptable manner with a workforce that can use and develop additional technology, because that's what's making things work. All the easy stuff's been found. It's now, both in the oil and gas industry, technology is what we're going forward with. Well, that technology requires a significant capital investments. So we need some sort of gas price that will support that, working together with regulatory and land issues to allow that development, having enough rigs, which surprisingly enough is a problem sometimes. We can't get enough wells drilled because we don't have enough rigs. And then given the volatility in the market, by the time we order them from overseas and they arrive, we don't need them anymore. So right now the rig count is way down except in the shale gas. And finally, a big question in the Rockies where I live is pipeline capacity. We have all this gas. We need to get it to market. Only about 5% of the country lives in the Rocky Mountain region, which is nice if you live there, but you've got to get that gas out to market. And pipelines take a large investment, a large amount of regulatory working with folks to get it out of the market. Similar situation is with trying to move electrons around the country. If you generate them in a new state, say in the Mojave, how are you going to transmit those electrons someplace? Similar situation of the gas story. So this is where we are in the gas supply picture. We think we have a lot of shale gas. It's located in a lot of basins. Everyone's excited about it. And things will calm down in the industry, I think. There's been an awful lot of promotion of this work, but there's been an awful lot of good technology that's been developed to get after it. So the Potential Gas Committee, the folks that have been doing this for a long time, think that the resource base is real from a geological standpoint, and that gas can continue to at least hold steady, if not increase more, to the nation's energy supply beyond the 25%. All the questions of infrastructure, the questions of price, competition is all yet to be resolved. An interesting side issue that's what happens with shale gas has to do with liquefied natural gas. LNG is the way to move natural gas from country to country across the oceans. It's a very, very much a thriving market for places like Indonesia, which needs more gas than they can produce, Japan, which is particularly gas hungry, China, and other places are importing a great deal of LNG. The United States, under Alan Greenspan's comments about LNG several years ago, allowed more tankers to be built and allowed more LNG terminals to be expanded in anticipation of a greater gas demand. Then along came shale gas, and all of a sudden you have this less expensive gas displacing the LNG. So right now we have a lot of terminals in this country which are sitting there very quietly, not taking a lot of gas from offshore. So the gas supply picture will change. You know, we have a lot of gas, but we don't have anything compared to Qatar and compared to Russia. Saudi Arabia, other countries have a great deal of gas. A lot of their gas is stranded. We have the market. So let's move forward here. Actually, does anybody need any terminology clarifications before I move on all of this? Reserves and resources. Okay, so next time you pick up the Wall Street Journal and they talk about this, then maybe you'll have a little more insight to it. If we had gone from 250 trillion cubic feet of proved reserves, which is roughly what we have, to 2,000 trillion cubic feet overnight, I wouldn't be teaching school. I would be out there trying to drill some wells to get that out. Well, let me switch gears on you. We think we understand the shales at a macro level. We know where the shale gas is. We have the technology to extract it. There still are a lot of surprises, though, in this natural gas that we produce down at the molecular level. And this is information from a talk that I gave at there's a group, the Goldschmidt Conference from the Geochemical Society out in Switzerland this summer. And what they're looking at these shale gas wells, and just like any other science, when things are happening and research dollars are being spent, we find out more information. And even if you find out something that's really basic research, which is what we desperately need, I think, you can go get the funding for it. So I'd like to show you some work that was done looking at the isotopic character of this natural gas and how it affects productivity and our predictions on how much gas we can actually get and how much we can use. So very quickly, I'm going to talk a little bit about carbon isotopes and then give you 3 examples of how these isotopes are not well behaved in shale gas systems, or they're not well behaved based on our conventional wisdom. So just a bit of background. If you go back to freshman chemistry, an isotope is nothing more than a nuclide with differing number of neutrons. So carbon is carbon. It's got 6 protons, and it's got all these electrons floating around there, 6 of them to match up, and 6 neutrons. Well, that's your basic garden variety carbon, carbon-12. The 12 being the 6 protons plus the 6 neutrons. And here are the neutrons and the protons in the nucleus in this little cartoon. About 99% of carbon on the planet that we inherited from the formation of the solar system is carbon-12. It's got 6 and 6. About 1% has an extra neutron. And that extra neutron makes it carbon-13. It's still got 6 protons, so it behaves like carbon. But that extra neutron, being 1/12 of regular carbon mass, allows things to separate in nature, and we call that fractionation. Now, when we get too many neutrons in something like uranium, it's radioactive, and that nucleus is unhappy and it wants to split apart. We don't have that situation with carbon except for carbon-14. You know, we can date Paleolithic campfires and things like that, but I'm talking strictly about naturally occurring carbon, the most common kinds they're stable. They're not going to decay on you. Mostly carbon-12 and some carbon-13. Here's a methane molecule. That carbon could be 12 or 13. It wouldn't really know the difference, but it's going to behave a little differently in nature. And here are the 4 hydrogen atoms surrounding it. In a moment, when I talk about dry gas and wet gas, dry gas is strictly mostly methane. Wet gas has the more liquid components, ethane, propane, butane, the stuff in the lighter, pentanes, and hexanes. So dry gas is either a result of being generated by bacteria as a metabolic product, and you probably know this as landfill gas, or if you don't take your trash out and you leave it out behind the frat house too long, you know, it swells up, and that's microbial gas. That's dry gas. Or it can be natural gas that has gone through such heat in a natural burial in the earth that these guys have cracked to methane. Well, it's easy to take samples for a gas isotopic thing. This is not a advertisement for IsoTube or Isotech. I haven't got a clue where they are. But it's very easy to collect gases when you're drilling a well. You can either collect them in these little tubes, and they call them isotubes, which makes it sound like it's a fancy way to preserve things, but those isotopes don't care. Just get them in a tube, seal them off from the atmosphere, run them in a very standard laboratory instrument, and you can measure the isotopic composition. They also sell you something called iso jars, which is a plastic jar with a little hole in the lid, so that when you put rocks in here and a little bit of water, any gas that's absorbed onto that rocks or in the porosity will evolve, and you can take a little bit of it out and run it through a gas chromatograph. So very simple analyses. Well, when you're drilling a well, sometimes we have what's called a mud logger on there. Drilling mud is simply the material we put down in the well to lubricate the drill bit. and to control pressure so that well doesn't flow back on us to blow out at the surface. And it's got a couple other uses too, but this drilling mud, as we're drilling that well, as we're drilling that cylinder or rock, down say 2, 3, 4 miles deep in the earth, gases that come out of the formation are entrained in that mud. And the mud logger, guy sitting there in a nice little trailer, hopefully with an air conditioner, depending on where they are, can take some of that gas out of the drilling mud that's helping you drill that well and measure that gas in just a real basic chromatograph. And we get how much C1, C2, C3, methane, ethane, propane. But you can also measure, and it costs a lot more money, how much methane, what the methane isotopes are like, and the ethane and the propane. The reason this works is shown on this diagram. This is a plot of either depth or increase in temperature. And this is a plot of the ratio of carbon-13 to carbon-12. And I won't go into the derivation of this ratio, but all it does is compare how much 13 you got, the heavy isotope, the extra neutron, to how much 12 you got, your normal garden variety carbon. And it measures this difference in parts per thousand. So there's not a lot of difference. There's just a little bit more carbon-13 in some gases and a little bit less and so forth. Well, what happens is bacteria make carbon that is very, very deficient in carbon-13. So it has this minus 80 number on the ratio. Bacteria want to break carbon-12, carbon-12 bonds. It's easier and they derive more energy from it. So they're not as happy with breaking carbon-13. So the gas that they give off as a metabolic product on some of these bacterial consortia is very deficient in carbon-13. When you make oil, you get more carbon-13 from degradation of the organic matter in the sedimentary rocks. But as you heat that material naturally in the subsurface, what happens is that the 12 bonds preferentially break, and you end up with a material that's more and more rich in carbon-13. So in a nice little laboratory instrument, mass spectrometer, you can measure how much 13 compared to how much 12, and it's a fingerprint. It tells you exactly what's going on in this gas, what its heritage was, and what its thermal history is, if you're smart enough to interpret it. And we thought we were, until we started looking at some of these shale gas systems. So that's the new part I want to show you. So why this works is, as the amount of carbon-13 increases, and as we measure that in the methane, we change the fingerprints and we can understand what's going on. Well, here's some data from the Barnett Shale. This is a group of rocks that gentleman, George Mitchell, worked on for over 20 years that now contributes about 5% from this one formation to our daily production. Normally, if you were to plot gas wetness, that is all methane here, versus the isotopic composition, in this case of the ethane, more and more carbon-13 up here, you'd get this kind of line. The gas gets drier as it gets hotter, and you get more 13 concentrated in the ethane. Well, that works out fine in a large area of this Barnett Shale till you get to a certain area, and all of a sudden those gas isotopes do something that no one predicted. And we're still having trouble understanding at a real fine level. Instead of going this way, getting heavier, they get lighter and lighter and lighter, and they never come back. That gas changes its composition, and it never comes back. You say, well, that's interesting. Who should care? And there is a reason to care, and it has to do with money. If you look at where these wells are, this part of the basin is where the well-behaved isotopic ratios are. And as you get over here, going over to the Washoe thrust faults, going deeper and hotter, this is that rollover area. Well, it turns out if you plot gas wetness, being very dry here, versus production over here, that the wells that don't have that rollover are never good producers. They're just never good producers. If you only knew that ahead of time, you could have saved a lot of money. As you're drilling the well, look at the gas, measure its isotopic composition, and say, we're out of here. Or measure it and say, this is a keeper, keep going. Well, poorly producing wells can be down in this area that are very dry. but they also have some organic carbon, hydrogen problems, and some rock property problems. And it turns out, whoops, excuse me, it turns out that the best wells are always up here. They're in that rollover zone. So if only we knew, we have this hindsight, that the best wells would be located there. So to summarize this little piece of the geochemistry, these high maturity shale gas wells, high maturity meaning higher temperature, are the best. We also see this in other basins around the country and into Canada, and they appear to be the most productive wells. And it's a question of whether cracking those bigger molecules, the ethanes and the propanes and the butanes, going down has increased the productivity of the wells. It's certainly increased the pressure, allowing these very, very difficult to flow wells to move on. And additionally, there's a line of thought using some very sophisticated imagery that says maybe the organic matter itself is becoming brittle and cracking at this nanoscale and allowing gas storage within that organic matter. So some unanswered questions. Well, if we just look at a single well, and we'll look at the Haynesville, these are wells that they drill these wells and they come in for 30, 40, 50 million cubic feet a day. That used to be the entire shale production from some fields in West Virginia and Kentucky in the old days. So here is a plot of going down through the geology. This is the formation known as the Bossier-Cotton Valley, and this is the Haynesville Shale right here. As you go down, the gas wetness is pretty high, and as soon as you hit the Haynesville, the gas is extremely dry. Similarly, as you go down, as you hit the Haynesville, the gas isotopes, which were very well behaved and would follow this normal maturity trend, snap back and again get very, very light, much less carbon-13. So a single well is behaving as you drill it, like the produced gas from the well in the Barnett. So there's a question of what in the world's going on. We know it's overpressure. Typical well, if you drill down, has about 0.45 psi per foot change. So you get about a half a psi, a little less per foot change as you go deeper. These wells have 0.9 psi per foot, almost the strength of the rock itself. So there's a lot of pressuring going on there. And we can explain the origin of that. If we go back to the Barnett and the Fort Worth Basin, we know from using fingerprints that we term biomarkers, we know that that Barnett Shale, I'm trying to speed up here. I got a lot to say, and I notice the clock is moving on here. It's a problem with being a professor anymore. You get too excited about this stuff. We know the Barnett Shale has actually sourced a lot of shallower oil fields. We can look at the shales, look at the organic matter, we can look at the produced oils, and we can fingerprint them, we can correlate them. So there's a lot going on there. However, if we go to where the Haynesville is, which is a beautifully rich, juicy source rock, it doesn't appear to have sourced any oils in the area at all. There's only one oil, and these data points represent hundreds of wells in Texas and Louisiana, with many wells behind each point. There's only one questionable oil that may have come out of the Haynesville. So it looks like the Haynesville is a closed system. It's keeping all its hydrocarbons in there. These things are cracking. They're causing this massive overpressure, and it is a massive overpressure, and they're enhancing the productivity of this shale gas dramatically. Now, it's not a simple matter of just drilling into these things and producing them. We typically drill down a vertical well, go horizontal, and go out for maybe a mile within these rocks, and then complete these wells 11,000 feet underground. So it's an expensive proposition. So that's two looks at the isotopes. One is that rollover where in the producing area you can find where the best wells are after the fact. But also drilling wells, you can find out what's going on. And then finally, permeability in shales is a big question. Permeability is the ability to flow fluids through these rocks, in our case flowing gases through these rocks. Shales, again, are notoriously low in that. We'd love to be able to know when we drill where the best zones are so we can put our stimulation treatments, concentrate our energy into breaking up this rock into the right zones. Well, the isotopes actually give us some insight into this. This is depth going down the wells. These are 100-foot intervals. There's about 5 samples per every 100 feet. That's a very expensive proposition to do 5 isotope analyses on the mud gas, the gas that's coming up as you drill the well, and on the cuttings gas, on taking the rock you've ground up, putting it in those jars, and letting the gas devolve off of that. So it's a very expensive proposition. And the laboratory that was doing this work finally asked them, why are you doing this? We welcome the work, but why are you spending tens of thousands of dollars just to look at one well? And the answer was they could find where to concentrate the completions. And this is one of the reasons this resource has increased so dramatically. Well, it turns out that there's a very large and a very measurable isotopic difference between methane, shown here in the darker colors, as you drill the well, just free gas coming up the wellbore in the mud gas, and methane that's adsorbed onto the rock, onto the cuttings over here. Very large isotopic differences. But it's not a set of railroad tracks. It's not equal all the way as you drill the well. There's some areas where the isotopic values are essentially identical. In this case, we're looking at methane isotopes, here and here and here. In some cases where there's a very large split. And it turns out from other information, we know that those zones where there's a very large split are actually the best zones in the well. And so the question is, how in the world do you explain this? How can isotopes tell you something about gas flow through very challenging rocks? So this is our thinking on this. Here again is the isotopic profiles. Gas in the mud log on the left being lighter, less carbon-13. Gas absorbed on the rock cuttings that you put in the little jar and you look at back in the lab on the right, more adsorbed gas. Well, as you drill the well, these are meant to be little bits of shale, and the blue is the free gas, and the red is gas absorbed on the shale. These shales, anything with a lot of surface area, has the ability to attract gas molecules to it and just sucks onto it. Instead of being in the pore space at a certain pressure, it's just a monomolecular layer lining these shales. That's one of the reasons we can store so much gas here. Well, if you have a well that has poor permeability, as the well is drilling, you get a little bit of free gas, but these rocks are so tight, these are so low in permeability, that the cuttings, as they desorb gas through time, because you've had big pressure changes, have a lot of free gas and a lot of gas absorbed to the cuttings, and you get sort of similar isotopic numbers. In other words, you're mixing free gas and cutting gas. Even though they started out here, by the time you get them to the lab, they're like that. And you can contrast that to a really good well, that when you drill that well, you get a lot of free gas coming up, shown over here, very light in carbon-13. And by the time you get the cuttings in the jar, you know, sitting on there working on the top of the rig in East Texas or in New York State or Pennsylvania, by the time you get them in the rig, most of that free gas is gone. So the gas that desorbs later is the heavier gas off of the cuttings, and it shows up over here. And that separation indicates zones of greater permeability, which have been calibrated against other more normal tools. So here's a way to use gas isotopes. It's expensive, but a lot of companies are doing it in a lot of shale basins in the United States and Canada because it seems to work. So this was, you know, pure serendipity. People doing basic research had no idea that they could use isotopes like this. So to conclude the isotopic part of my talk, we can correlate the shale gas well performance to these gas character anomalies. And we care because we'd like to continue extraction of this resource. We'd like it to be a steady or increasing flow of natural gas. So the more we understand about that from a science standpoint, the better we're able to extract this. When the ethane isotopes roll over, that Barnett example, where the gases get lighter and lighter and never change across an entire field, we know that's the best productivity. You can also get that from propane isotopes, but often these wells get so hot that all the propane is cracked to ethane, and you don't have much left. If you look at a single well, the Haynesville example, you can get a situation where the ethane isotopes go along a normal maturation trend, and they snap back, and they keep on going with depth, and that's where you want to stimulate your well. That's where you want to get into it. And finally, to even fine-tune that a little better, looking at the isotopes in the mud gas and look at the isotope in the cuttings in the headspace of these jars, we can determine the best zones in order to complete an individual well. So that's the story on shale gas from 1821 to 2010. Now, one thing that you'll see in the paper is that people talk about us having a 100-year supply of natural gas. And all they've done is taken work like the work of our Potential Gas Committee, say 2,000 trillion cubic feet with proved reserves, and they've taken how much gas we produce a year, say 20 trillion cubic feet, and they've divided. And that is really not what to do, and our committee does not do that, because this gas is in a natural system. We have a variety of environments. Some of it's very high quality in pretty well-behaved rocks, we understand. Some of it's in rocks that are much more challenging to extract. So it's not a simple matter. It needs a lot of good science and engineering attached to it, and that's what we're hoping for in the future from folks like you as students and future graduates, as well as other researchers around the planet. So, thank you for your attention.
Okay, questions? How about back over there?
Yeah, can you talk about the potential gas resource in offshore areas that are currently restricted for drilling?
Okay, I can do that. We, in our report, in these 89 provinces, if an area has a moratorium that's set to expire, such as the Eastern Gulf, west of Florida, south of Pensacola, we still have the geologic information from Minerals Management Service as well as from companies, and we publish that estimate, and we publish it, in the geographic area. If an area is under a permanent moratorium, Yellowstone Park being an example, even though the rocks aren't the right kind of rocks, then we would never make an estimate of that. So we include places like offshore California and offshore Atlantic, although we don't have very modern data. And those are denoted by folks in the know as where they are. If they expire, we may move forward. The Atlantic's a great example of that. The Canadians drill right down to the border and have reasonable productivity up there, more in oil than gas. If you look at a map of wells in Lake Erie, you see all these wells in Lake Erie. And I've been water skiing in Lake Erie. I didn't remember any wells out there. Well, it's the Canadian border coming down. So the rocks are right. It's just a matter of we're not allowed to drill there. We don't assess under Lake Erie. That's permanently off limits as far as we know, for example. Yes, sir. Or Lynn, excuse me, Sally.
Go ahead. Yeah, no, go ahead. Yeah.
In terms of your 2,000 TCF estimate for potential gas leakage, should I think of that as sort of total gas in place, or is that more sort of a 3P estimate? Okay. And secondly, as you get closer to thinking about the next estimate, do you have any sense is that likely to be higher and grow by something as the past go around?
Okay. Both good questions. We don't estimate gas in place. The way this committee works, because they work these basins for a living, they have access to private company data as well as public data, and we do things on a formation basis up. We don't model the resource base. We go beyond proved reserves, which have probable, possible, potential, 10, 50, 90. We go on proved reserves. We're what's left after that. We do have 3 categories of gas which correspond to existing fields, a possible new fields, productive formations in that basin, and speculative or frontier, which are typically deeper, non-productive formations. So we're beyond that. So I think I've addressed the first part of your question. The second part, should it get bigger? As you saw from the one graph, the amount of resource assessed has slightly grew up to 2006 till the shales became more productive, even though we produced 40 TCF between each assessment. Coal bed methane wasn't on that chart. It came back in the very late 80s into 1990. We would anticipate as we evaluate more shales, if the industry's drilling it so we have the data, and if the productivity holds up, that we may see a net increase. I don't think we'll see the dramatic increase because it's really driven by the Haynesville and the Marcellus. And when you add 1 trillion cubic feet a year in real reportable data, not company propaganda, but actually DOE information coming out, then that's real. We'll see how solid that is into the future. I'd anticipate a change, but nothing like this year.
Okay. All right, how about back over there?
So So I just have a basic question about geology. So the shales that we're talking about, are they the same shales that we use as cap rocks for CCS? And if that's the case, then do you see any kind of competition in the future between applying CCS because you're fracturing completely on rock and the implementation of the shale gas technology?
Okay. Shale is sort of a garbage term. Just a very fine-grained rock. Geologists talk about mud rocks and clay stones and so forth. The shales that we produce are not good seals from the standpoint as we want very low clay content. For a seal, you want high clay content. You want those clay layers, the illite, the smectite, etc., to be laying like this so they form a nice broad seal under pressure from the overburden. Additionally, on a percentage basis, the amount of shales that we actually touch looking for gas is a very small percentage of the rock column of shales that exist. Philip? Yeah. I've been looking at Philip Wolfram since this talk started. Since I tried to give my introductory remarks, I said, my goodness, he looks like Philip Wolfram, who I had as a freshman at Colorado School of Mines, and who wanted to be a geologist, and then he went to the dark side and went to civil engineering. But I'm looking out there thinking, oh, if that's not Philip, that's his brother. But I've met your brother. So I knew that wasn't it. So, hello. So excuse me here. I'm just looking at this, and you're not even grinning or waving at me or anything. Very professional, very professional.
Okay, Lynn, how about,
So you've no doubt heard all the talk about how there's now so much gas available from the shales that we have the option, for example, of repowering lots of old coal-fired units as with natural gas, getting a boost in efficiency and a reduction in the amount of carbon in the fuel, and therefore a reduction in the CO2 emissions. Now, whether that and the question of whether that works in the long term depends on whether the kinds of production can be sustained and it actually increased to accommodate the additional energy demand. And so my question for you is, I mean, you're probably in a better position than anybody else to have some sense of what fraction of these resources actually do get converted into proved reserves that will be the kind of reserves that actually do run a power plant. So could you just kind of strip away all the propaganda and advocacy that's going on and tell us, is it realistic to expect that you really can accommodate more or less any amount of increase in demand for natural gas for electric power generation?
Well, any amount, I'd say no. We have the industry in this country has produced about 900 trillion cubic feet plus of gas. We don't have good records, but we do know that we've produced at least 900 trillion cubic feet of gas in a reasonable time frame going back, X number of decades. Gas didn't come into its own until after World War II as far as large volumes. The interstate pipes were put in place in the 1960s out of South Louisiana, Texas, up to the Northeast and all. So compact history. We do know that if we go back to estimates of that time, not really Potential Gas Committee, somewhat the committee, but other estimates, we've produced all we thought we had. So our view of the endowment changes as we get smarter. And there have been surprises like the Haynesville and the Marcellus and other shales, the Fayetteville, taken a lot of work and a lot of effort and a lot of money to get to them, but there's been some duds too. There's been particularly the Baxter Shale in the Green River Basin and the Caney Shale in the Arkoma Basin have not worked. And a lot of it's too much clay. They don't fracture well. So it's not a simple matter of taking how much shale we have and dividing. So pulling on that gas to accommodate any number of retirement of coal plants is not something that can be guaranteed. The geological endowment says we got an awful lot of gas. And we're finding more gas. Our understanding of the endowment's increasing. But to get at that gas, and that was my earlier comments in summary, some of that resource base is very high quality, some of it's not. So it's not something as simple as having a policy to say, let's go do it.
Can I add to that just a little bit? With electric power research, we just done quite a bit of work on that. One concept is that they have core areas, and they have what they call goat pasture areas in each of these areas. So you might get 3 billion cubic feet in a lifetime projection for a well, where we have to go 25 more years before we're going to know whether or not we got that 3 billion cubic feet. So it's still an estimate. We're at a very early estimation stage in every one of these basins. So let's say a really good well is 3 billion. People have up to 6 billion. They've been muttering up to 12. But if you're spending $3 million to $8 million to drill a well and frack it maybe multiple times over its life, and you end up with only 1 billion cubic feet, well, suddenly your economics have changed terribly. But you're going to need a lot of those 1 billion cubic footers to get at all the quantity of gas you need to, say, replace the power plant infrastructure. So when you start looking at what kind of demand we might be able to sustain in our country, we're maybe in this 20 to 23 TCF mode now.
23.
And so we figure, let's say it's 2025. That's not that long from now. And maybe our demand could grow to 25 TCF. I don't think anyone sees a big problem with that.
Not with that.
But we see, let's say you go to 28, 29 cubic, a trillion cubic feet. Then we're in a little iffy mode, and that's also when you're importing some LNG, but competing with the rest of the world, who's also discovering gas as a commodity that they want to monetize, not just send to the United States. And then if you get up into over 30, we're reaching a point where we're beyond goat pasture. And so if you let your demand accelerate beyond your knowledge, you're really trying to bet on and put in the bank stuff you're taking a big risk to say you think you can get that at an affordable price that anyone would want to pay and buy electricity for. So all of a sudden we're competing and buying gas at international oil prices, which becomes an economically crushing thing for the U.S. economy. So as long as we can keep gas price under oil, there's still hope for commercial use in large-scale industry, I guess. But those are roughly where I see the volumetric trade-off.
Yeah, one time, Lynn, the federal government had predicted, EIA, 30 trillion cubic feet, 30 trillion a year by 2030, something like that. As we got even closer to that, as the price of gas went up, we had a lot of demand destruction, fertilizer industry collapsing, et cetera. So it's a fine-tuned thing, and it goes way beyond the upstream realm of geology that I'm comfortable with to what's down there and what's replacing what. And then, of course, you enter into the policy, and my home state is West Virginia, and they've had a lot of power in the past on coal research and so forth, so don't know.
Okay, let's over there.
Yeah, my question was regarding water usage data. I've seen some data on how much water on average it takes to drill one of these wells and then do the fracturing. Is there any data out there, especially for the newer explorations and resources that have been tapped, regarding looking at water usage, especially considering the variability among production on different sites, and instead of looking at just the total amount of water usage, how that water, for example, that water usage per unit of energy produced from the well. So, do you have any data regarding that, or know of any resources?
I don't know of any resources. I had heard your comment before about water usage per unit of energy. And since we're dealing in natural systems, it's wildly variable as far as what you're going to get, the good wells and the bad wells. It's an interesting topic. I don't know if you would go to the oil and gas conservation commissions, but if you go to a place like New York, Pennsylvania, they're not set up for this. They don't have this data. There's a young lady I've been talking with that's at Bucknell doing a senior thesis looking at frack water quality. So she's gathering samples from people. So it's out there, and there's some information behind it, but she has a lot of trouble, getting representative samples and so forth. The best thing to do might be to approach these conservation commissions in states that collect these data, like Texas, and just see if you could have a chance at that. But the Marcellus, for example, in Pennsylvania, New York, those folks are not used to having wells drilled. And so there's some real regulatory challenges, and there's some real fear, some of it probably justified based on the horror stories they may have heard. You only hear the bad news and not the good news. So there's a challenge getting new data from some of these folks that really aren't set up for them. Pennsylvania has a 5-year hold on the data. So if you give them the data, they don't have to tell anybody for 5 years. That doesn't help us.
All right, how about here, and then back there, and then that will be the last one.
Any sense of how much is available in Canada and Mexico via pipeline?
Yeah, our report looks at what those countries think. We don't assess Canada. We had a sister organization called the Canadian Gas Potential Committee, but they have folded, lack of volunteers. Canada's gas supply in the Western Canadian Sedimentary Basin, which is where most of it's concentrated, has been going to smaller and smaller fields as they drill. So that's become a problem, that the new fields they found are nothing like it was in the glory days. The Mackenzie River area is high potential up there, but a lot of that gas will go down more than likely to upgrade the tar sands. So Canada's fine. They used to give us about 3.8 trillion cubic feet a year. Now it's down to about 3.2 because their gas supply picture is not going up, except for the hope of the shales, the Horn River shales and other shales in British Columbia. But you have some real infrastructure issues to get up there to get that gas. But there's nothing wrong with the rocks or the technology. So you're going to see an increase on that. They also are in fairly early days of coal bed methane. They're actively going for that. It's nothing like our San Juan Basin production, but then nowhere in the world is like our San Juan Basin production. So they have greater potential in the unconventionals, as yet not quite as developed. Companies like Talisman Energy, looking at the Horn River and the Musqueam and other shales, it's strong hope. But Mexico, it's hard to get information out of them. We've had Mexican observers on our potential gas committee, and they've literally disappeared through time as far as their companies. We don't think down an alley or anything, but you know, the mail's returned and so forth. And their situation is a lot of their gas fields are undercapitalized, and they concentrate so much on that heavy oil that they've got, that high sulfur oil, and working on that gas is a poor sister. Typically, 10 years ago, 5 years ago, to be at net zero between the Mexican border and the U.S. on gas. And now we're a net exporter to Mexico at the moment. But they have refineries and so forth. So Mexico's a lot quieter.
For more, please visit us at stanford.edu.